Hey everybody, thanks for sticking around. I am the last person standing in between you and the pub, so we're going to get to it. The title of this talk is Braitenberg And The Browser. Valentino Braitenberg invented Braitenberg vehicles. So we're going to talk about Braitenberg vehicles, and we're going to talk about specifically how to recreate Braitenberg vehicles in a browser using JavaScript. And we're also going to talk about some of the broader concepts that Braitenberg illuminated when he created the vehicles. Really quick, yes, I'm a software engineering manager at Spotify, and you can get in touch with me on Twitter at Talent Events. And you can find all the code for the demos you're going to see at this repo. A quick note about the code, it only uses vanilla JavaScript, HTML, CSS, and DOM. There's no Flash, Canvas, WebGL, Java, any kind of rendering extras. So this is Valentino Braitenberg. He was an Italian neuroscientist. In the 1960s, he was interested in studying how human beings developed reasoning and intelligence. And instead of starting with human beings, he started with insects. And he was looking at simple brains for the clues to our cognitive evolution. And he was really careful about his methodology. So he wanted to look at the mechanics and the inner workings of simple systems as a path toward answering larger questions. So if he could understand how our brains evolve, he'd have a better understanding of how our brains work. And in the 1970s, he published this book, Vehicles, Experiments in Synthetic Psychology. And in the book, he performs a thought experiment. He imagines 10 hypothetical vehicles. And these vehicles are the famous Braitenberg vehicles. There's one flying over my head right now. So, each vehicle has one or more sensors and one or more motors. And the first vehicle simply has one sensor that's tuned to pick up temperature. And it's wired directly to a motor so that when it's around hot things, it sends a stronger signal than when it's around cold things. And the effect of this, if you were observing this vehicle, it would slow down around the cold areas of its environment, and it would speed up around the hot areas. As the vehicles progress, they gain increasingly sophisticated sensors and motors and wiring. So vehicle 2A has two sensors that are tuned to pick up light. And they're wired, they have same side wiring, so they're wired to motors on the same side of the vehicle. And as the vehicle approaches a light source, the sensor that's on the near side of the vehicle, the sensor that's closest to the light source, is more active than the sensor on the far side. And that means the motor on the near side is more active. And this vehicle will steer away from its light source and always avoids light. And another version of this vehicle uses cross wiring. So the sensors are wired to motors on the opposite side of the vehicle. When the vehicle approaches a light source, the sensor on the near side is more active than the sensor on the far side, but the motor on the far side is more active, making the vehicle turn toward the light. So if you were observing this system, you might say the vehicle on the left, 2A, it doesn't like light, it always avoids light. And the vehicle on the right, 2B, it likes light, it desires light, it always turns toward the light. Well, as observers, we would be wrong. We would be wrong due to a law that Braitenberg calls the law of uphill analysis and downhill invention. Basically, this means that we tend to overestimate the complexity of the systems that we observe. Now, as designers and inventors, we know that these vehicles' behavior are dictated by a very simple internal mechanism. But as observers and as human beings, we tend to attribute qualities to their behavior, like fear, aggression, like, and dislike. And it's this interpretive space that's really the magic and the appeal of Braitenberg vehicles. Because as an observer, what's going on underneath the hood is completely open to our imagination. And Braitenberg collaborated with an illustrator who provided these drawings that really show how far our interpretations can go. This is my show with Albrecht. And it's really interesting that they collaborated on a book because it vividly juxtaposes the idea of the inventor's perspective and the observer's perspective. Alex Weaver is an inventor, and you can read more about his creations on tinkerlog.com, but he creates Braitenberg vehicles out of Arduinos and photoresistors and servos. And I think it's interesting to see one of these vehicles actually work. So that vehicle has an inverted wiring in the sense that its wheels, its motors, are most active in the absence of light. And then as it gets closer to the light, they slow down proportionally. And the effect is that the vehicle seems to be in awe of the light. This is another vehicle that's even smaller. It's about the size of a euro. And these are kind of neat to watch. These have exactly the same wiring. It's kind of nice to see them in a pair. You can imagine coming home to your apartment and turn on the kitchen light and seeing us scurry out to the cupboards. So this vehicle has a different type of wiring where there's no dampening on its motors. Whenever it senses light, it goes all out and doesn't try to slow down. And the effect is that it overshoots the light. It overshoots its target and has to come back. And it seems really pissed off because he's very, very aggressive. As a JavaScript developer, when I started looking at these vehicles, I thought, all right, well, how can I create these in a web browser? How can I explore these ideas with JavaScript? So I'm just going to show you a few examples. So we saw the first vehicle. It has one sensor that's tuned to temperature. And it slows down around cold things, and it speeds up around things that are hot. Now the blue represents something cold, the red represents something hot, and the sensor's range is represented by that dashed line that is around the vehicle. Now you can, if you saw this in nature, if you're observing the system, you'd say, okay, well, this vehicle can at least move. It can get around its environment. But it seems to kind of lack an awareness. It certainly couldn't really navigate. Now we saw vehicle 2A. It had same side wiring. And it always turned away from what it was stimulated by. That's what we have here. Now I didn't want to just have one vehicle, so I have kind of a set. And they sometimes, like, there you go. So the yellow nodes represent light, and you can see that the vehicle seems to be a little more aware of its environment. It can navigate its environment and actually can kind of get itself out of really tricky situations. Now vehicle 2B had the crossed wiring. So vehicle 2B will overshoot and turn toward what it's going after. I've coded this to actually destroy the stimulus once it's hit it. But now, this is something different. The vehicle can navigate its environment, but it almost feels like a rampage. And then we saw what happens when you invert the wiring. So that in the absence of light, you're excited. Now, love is a strong force. You gotta get him away here, and he'll get ensnared in a second. by what he pursues. Now, we don't have to have such extreme reactions to the stimulus. So what we can do is we can dampen the signal to the motors in proportion to the distance from what it's being stimulated by. And with a vehicle that has same-side wiring, this is kind of nice. You get something that feels like it's exploring its environment. So it doesn't have some kind of extreme reaction. It's okay getting close to what it's stimulated by. But its movements are much more subtle. And this vehicle feels like, yes, it definitely has an awareness of its environment, but it feels like it has intent. It feels like it's searching for something. Now, the neat thing about Braitenberg vehicles is you can stack sensors. You can combine sensors and throw in a bunch of stimulus. Okay, before we get there, I have one more sensor. You can custom build sensors. I've custom coded another sensor to be curious. So this sensor looks for the midpoint. It runs toward the midpoint and then turns abruptly away. So it has this effect of appearing like it's curious about what it's stimulated by. If you throw a bunch of these in a field, it gets pretty schizophrenic. They look incredibly indecisive. I don't know what those guys are doing. But yeah, they can get kind of in this endless loop of indecision. But yeah, like I said, you can combine all of these and throw a lot of stimulus in the mix. There we go. And now we have something entirely different. So as the vehicle makes its way around its environment, it knows what it wants and it knows what it's pissed off at. And it almost feels like it's making choices. Like it has a sense of values. And at this point, you stop seeing the individual rules and you really see the emergent behavior of the combination. So how do we do something like this in a browser? So we've heard a lot about simplicity today and the value of simplicity, and I think it's a good exercise to start very simple. And we need to define what is a natural simulation before we try to build the bare bones of one. And I believe that this definition, or I like this definition, it's a collection of agents whose boundaries of autonomy appear be defined by natural forces. And this idea of appearance is really important. Because remember the law of uphill analysis and downhill invention. The observers can be easily persuaded. And that's really nice because you can see that what we're doing here is working with really simple rules. So what we don't want to do is build a very hyperactive physics engine. We don't want to build Box 2D or something. We want to build a system that just simply sums all the existing forces in our system and then applies those forces to all the objects in the system and then determines the location of those objects at any point in time. And I'm crediting Daniel Schiffman on this slide. He wrote a book called The Nature of Code, and my approach is based on principles that he outlines. And I would definitely recommend checking out the book if you're into this stuff. So I'm going to call the basic framework for natural simulation super simple sim, and we're going to talk about the classes and the responsibilities. There's only 3 classes. There's a system, and we're going to set up some initial world conditions, and we're going to use the document body to define the view. It's going to be the view layer of our world. We're going to define a render loop using request animation frame. And we're going to draw items on the screen using CSS. And what we're going to do is convert the visible properties of our objects into CSS and concatenate them into a long string, tack on the style property of some DOM elements. The second class is going to be an item class, and the items represent all the objects in our system. And we're going to create div elements as our view for our items. We're going to assign visible and non-visible properties. So a visible property would be color or scale, and a non-visible property would be something like mass. And then we're going to define a step function. And the step function is where we're going to determine at any point in time where should this object be. And then we're going to use vectors. We're going to use a vector class to help us actually do that. Vectors provide properties and methods to position items. I think it's worth talking about vectors to make sure we understand them. I want you to think of a vector as an offset. It's just an offset between 2 points. So in this case, I have vector A, and I also have vector B. Now vectors imply a magnitude. So I can talk about vector A as being greater in magnitude than vector B, and you can see that visually because vector A is longer than vector B. But let's say these vectors represented forces in our system. Let's say that vector A represented steam coming out of the ground, and vector B represented wind blowing down and to the right. What would it feel like to stand in this system? What would the sum of all those forces feel like? To do that, we just add vector A to vector B, and it's pretty simple math. We're just taking the x property of vector A and adding it to the x property of vector B to get 5, and then we're getting -2 when we do the same with the y properties. Now we have a new vector, and we can apply that vector as an acceleration to the items in the system. I think it'd be worth talking about the step function in our items as well. The step function is where we're going to do what we just talked about. We're going to sum the forces in our system and generate an acceleration. Now, if you remember from physics class, an acceleration is just an expression. It's an expression of a change in velocity. We can add the change in velocity to our existing velocity and get a change in location. Velocity is just a change in location. And then we can add it to our existing location to get a new location. What this means is that at any point in time, I can sum the forces in my system to generate a new velocity, add that to my location to generate a new location at any point in time. All right, so let's see that actually work. So this is a very simple implementation of what I'm talking about. You see you can't see it in the back, there's a little item starting out in the middle. The only force in the system is gravity, and it's straight down, and over time, the item changes location and appears to be affected by gravity. So I think it's worth looking at the HTML file that's driving this, just to see. We've imported our framework, the super simple sim. Zoom out again. And we've set up our system with some initial conditions, passed in a callback to add an object, and then we've kicked off a render loop. So let's look at the system class. We look at the setup. The initial conditions are gravity pointing in one unit straight down. Wind, there is no value, so that's why you saw our object not be affected by wind just by default. And then we called our function that we passed in, and that added an object that was an instance of the item class. And so I'm just passing in the name of the class, and this condition is met, and we add an instance to a records array. In the loop function, we simply loop over the records array, and we run the step function that I was talking about to generate a new location. So now we have all new x and y properties, and we call a function to draw our items. The draw function, these guys actually point back to the system and passing in the visible properties of our objects. And then using a utility function just to concatenate a bunch of CSS. There we go. You can see that it's just a long string of CSS that gets tagged on to the data. So what's kind of fun is then if I don't have to make just one of these. So I can make 180, and I can randomize some properties so that we get random scale and some randomization in the color. Get something that looks like this. So now we have 180 items rendering at 60 frames per second, And we're staying kind of true to some realism here with the slower objects being the bigger objects and having a bigger mass and so on. So I talked about combining forces. So let's introduce some wind and see what happens. So to introduce some wind, here's the wind HTML file, and you can see here, all I'm doing is just overriding the default value for wind, and setting the wind to 1 unit to the right, and then slightly down. When that gets combined with gravity, you can see that now it's falling a little faster down, and then collecting in the lower right corner. So you can do interesting things with vectors just on initial conditions. So in this little simulation, to create just like a fireworks effect, all I'm doing is setting for the smallest objects, their position is inversely proportional to their size and their position away from the center, and then I'm just randomly rotating their initial location vector, and the result is the bigger objects stay in the middle, and you have this kind of nice mountainous clump of div objects at the very bottom of the screen as they come to rest. So you can see that you can apply vectors as a constant acceleration, but those vectors can change, and I can apply a new vector every time, in every frame, for a new acceleration, a new collection of forces. And what I'm getting at is, I can make these objects follow my mouse just by implying that the distance from the object to my mouse is a force. And I can then, it's a vector, and I can then apply that to the objects. And in physics, we have this formula, it's F equals ma, right? And so I'm dividing that force by the object's mass, meaning that the smaller objects can move faster toward my mouse. And you get this nice kind of flocking effect with these divs. So what's kind of fun is that this is, since we're working with the DOM, you can kind of play around with our item. This is the item class that I was talking about. You can see here that I'm defining this world as a document, as a document body, and just appending it after I created an element to represent it. But I can change this element. So what if I changed its root element to input type radio? I get a nice set of bubbles. These are actual radios. What's fun about this is these are actually clickable. So if I get 2 going, it kind of looks like a monster with 2 eyes. And you can do the same thing with select boxes. Get kind of 2 sets of eyes where you would click that box. Apparently select boxes are really hard to render because it's kind of slow. We're going to change these back to divs. There we go. All right, so now we have a natural simulation running in our browser. We can see it's pretty simple. There's just some real basic computation going on there. To do something as complex as what we saw in the Braitenberg vehicles, we just add classes. So when we start building out the sensor classes and scripting the behavior, all we're doing is what I was doing with the mouse. We're just creating new forces to either repel or attract our Braitenberg vehicle. And I think that it would be really interesting, Braitenberg simulations and experiments that you see typically leave the inventor out, once they start rolling, right? So, you see a bunch of vehicles set up and the lights are turned on, they just kind of do what they do. But it would be really interesting to interact with that system, in real time. So I'd like to explore how we can interact with a Braitenberg simulation and natural simulations in general in 3 ways, using 3 inputs into the browser itself. And the first one is going to be really easy, the mouse. We just kind of saw that. If we're going to interact with a natural system, we want that interaction to appear as natural as possible. And the mouse is kind of an unlikely candidate for this because, for the most part, it's kind of like having a weird little hand that just kind of taps on things. But we can do something really interesting with the mouse is we can express acceleration. right? So let me show you real quick. Remember when I was talking about vectors? All I'm doing here is creating a vector with an origin in the middle of the screen. And you can see that the magnitude of the vector expressed there in the lower right, no matter if I have a positive or a negative location, my magnitude is always positive, and you can see that it's actually bigger when it's longer. If I take a group of objects and then just simply accelerate them according to the vector that I'm creating, I get this nice effect of being able to kind of direct the items around in the simulation. And when it comes to a Braitenberg simulation, I can do just that. So in this one, I've left the mouse reference in there so you can see what I'm doing, but I can steer the vehicle around and it'll still pick up what it's stimulated by. And sometimes that force can override the force that I'm trying to apply. But at this point, I'm very much an active participant in this simulation that I've created. And this can be kind of addictive. So. Alright, so we can mess around with the mouse. So we saw with Alex Weber's experiments, they're like a lot of other experiments with Braitenberg vehicles. They use light as the stimulant. And I thought it'd be interesting to explore using sound as a stimulant. Because to me, sound, it's a little more interesting. We kind of take it for granted, right? We use sound kind of almost unconsciously to pick up what's going on around us, and it inspires certain behavior. So to do this experiment, I created two of these. And these are essentially wireless microphones. They're basic microphones that are wired into an Arduino. And I'm using an XB to make them wireless. But I'm also using Node serial port. The Node serial port is just a node module that lets me listen for data coming across the serial port from the Arduino. And then I'm passing that data to the browser via WebSockets. And these microphones are tuned to a specific frequency. To show you what I mean, this is what I'm about to do. So you can see that as it changes frequency. Alright. So let me get this guy on. Got a tone generator. And I've got a simulation. Now I've turned only one of these on. As I change the frequency, I can really excite that attractor as I approach the microphone. Just kind of fun. And I have this idea for doing some type of flow control. So if these particles are flowing one way, I can excite the attractors to continue to flow the opposite way. So that's kind of like if we had one ear, right? But a lot of things that we encounter in nature have two ears. Let's see what happens if we do this in stereo. So if I have two nodes, I should be able to alternate what's happening here. Cool. And then we can do this in a Braitenberg simulation. So I can pin certain types of stimulus to either one of these and try to rope in this is almost like if I was there yelling. So I'm yelling, and then I can yell over here, and kind of call them this way and that, get them together. It's fun. Then if you have a whole field of these, you can just kind of see the exaggerated effects. So have them all come on. Whoa. So I know that tone is a little irritating, but I was trying to be very obvious about what I'm doing. I think that there's a lot of possibilities with that. You could use all types of audio analysis to pick up, the magnitude of the audio that you're hearing, and I'm going to continue to play with that. So what if we wanted to actually get our physical bodies involved in a simulation? We all carry around probably a mobile device that has some type of accelerometer or gyroscope on it, right? And if Braitenberg vehicles are really just a stack of sensors, then why couldn't we just turn what is essentially a stack of sensors, our iPhones or Android phones, into Braitenberg vehicles? So to do this, I created this little enclosure and module. It's a Bluetooth shield sitting on top of our Arduino. And kind of the same thing is happening. I'm using no serial port to then pull in accelerometer data and gyroscope data from my iPhone and then passing it off through WebSockets to the browser. For a close-up of what's going to happen, I wrote just a basic utility iOS app just for myself that will then throw across different information about the accelerometer and gyroscope. I want that run, and I'm going to set this up. All right. So I'm going to turn that node up. Stop that run. Bear with me for 1 second. Alright, so we plugged in this little module that you saw in the video, and I keep bumping something that loses the video. Apologize for that. Alright. So if I connect to this module, right. So you have to imagine that all these objects that are in this are sitting on my iPhone. And as I rotate my iPhone around, these guys will move accordingly. And I'm going to go back to face this thing. But now, instead, we saw that we defined gravity as just this arbitrary number. It was just 1, right? Now I'm actually using gravity. I'm sending over the gravitational force that this iPhone feels. And that is especially realistic and pretty fucking cool. I got started making another one, and it turned into this weird kind of worm chasing a beach ball. But at the same time, it was kind of cool, so I kept it. But doing this is actually really fun and a big thing to make these different versions. So this is tracking the gravitational force that this phone feels. But there's also other things we can do. We can send the phone's absolute position to the simulation. And so in this one, what I'm doing is I'm just rotating my phone, and it's just basically dialing up and down the attraction force in this simulation there. That's kind of cool. But absolute position can do other neat things. So if we ever wanted to fly one of these little guys around. So now I'm just tilting my phone to fly around a little autonomous vehicle. This is not so autonomous anymore that I have control of it. I can kick them around. I can add an action button so I can do things like this. Fart. So then, what do you do with a Braitenberg simulation world, yeah, you can take control of your object or your vehicle, and everything's kind of still applies. They're attracted, and that attraction force to something that's stimulated by can override what you're doing to it, but you can try to avoid them and so on. So now, we talk about how do we kind of inject ourselves as influencer in the system. This actually feels pretty committed. All right. So we've kind of crossed a line here, right? We've gone from inventor, right, where we're creating simulations and we can actually participate in simulations. So why don't we go all the way over to the other side of the observer? How can we create a natural simulation and then jump into the role of the observer and just watch it as an artifact of the simulation? It's not something we're going to interact with. It's something that lives out on its own. And really, how do you create a natural simulation in the browser and output it to video? That's what I'm getting at. And to do this, I had to change my render strategy. It's still using the DOM, but it's primarily using CSS box shadows. And it sounds weird, but stick with me. What I'm going to do is divide the browser window into 8 pixel by 8 pixel squares, just a grid. And I'm going to put one DOM element in the top left, and I'm going to hide that DOM element by giving it a width and height of 0. What's cool about box shadows is that if the parent has no scale, you can still see its box shadows. And this box shadow I've just positioned so that using the X and Y offset. And a key thing here is the scale, is the spread property. It's 4 pixels, which is 4 in each direction, so it's 8 by 8. Fits nicely into our grid, and I've given it a color and so on. So there's some other nice properties about box shadows. I don't have to have just one. I can have n number of box shadows. And like I said, they can have a 2D location relative to the parent. You can have a blur value. And a blur value is really interesting, as we're going to see. Like I said, the scale property can be translated into their spread property. And their color can be displayed with RGB or HSL, which is hue, saturation, and lightness. And that's really interesting. They can also carry an opacity that we can set. So then if I want to create shapes with box shadows, it's just a matter of positioning them where I want them. And then if they want to create animation, they want to create natural simulations with box shadows, it's just a matter of positioning them where I want them over time. So I had an idea. I'll show you some examples. So this is a natural simulation running purely with box shadows. You guys see that? These box shadows are chasing an invisible target, and they're exhibiting this flocking behavior. And it's kind of subtle, but I'm mapping their velocity to their blur, so they get blurrier as faster they travel. And they also lose saturation and gain some lightness. And this idea of motion blur I thought was really interesting. And I wanted to create something that was really kind of all about the motion blur. So I created this, and you can see that when they hit this invisible barrier, they suddenly stop moving really fast, and they get sharp, and they gain their saturation back. But otherwise, you can see that I have this kind of cheap motion blur effect for free. And the reason why I took this approach because I wanted, in my mind, I thought you could get a graphics program to recreate this simulation frame by frame, because really the data is so well structured and there's not a lot of it. It's not inconceivable that you can just record the data, all the properties for all the objects at every point in time, and then automate a task to render video. And luckily, it turns out that there are 2 very important components to this process that exist. One is Photoshop, and one is Node.js. So with the new version of Photoshop on Creative Cloud, you get something called Adobe Generator. Adobe Generator allows you to script Photoshop actions using Node. What you're essentially doing is creating a Photoshop plugin using JavaScript. And And I wrote a separate Node app that just recorded all the data at every frame for every object and output that to a JSON file. So I had a lot of JSON files. One JSON file represents the frame. And then I dumped them into Adobe Generator. Adobe Generator then fired off my plugin that walked Photoshop through recreating the frames. And the nice thing about this is, first of all, I can create it in any resolution I want, which is awesome. I chose HD. And I can use Photoshop filters. And the one I was really most interested in was motion blur. Now, I liked the motion blur I was getting with the CSS, but it's kind of a fuzz. It's just kind of blurry in all directions. But it should be blurry in the direction it's traveling. And if I pass Photoshop the velocity, it can derive the angle that it needs to render the motion blur in. And so I can actually get objects blurry in the direction that they're traveling, which is much more accurate. And then I render all the frames as video. Let me show you an example. Now that I'm not bound by the browser's limitations, I can actually add in a lot more objects. And you can see that the Photoshop filters are a lot nicer than what we were getting with the CSS. This is the other piece. See that I can add a lot more particles, and the motion blur is actually true. It's much more accurate. This photo is from a documentary called Particle Fever, and they follow several physicists around the Hadron Collider at CERN as they're conducting particle collision experiments. And it introduced me for the first time to experimentalists versus theorists. So there's experimentalist physicists that create experiments, and they have a very inductive method of trying to accomplish what they're doing. They start very small and then work their way up toward a theory about how the natural world works. And then the theoretical physicists start from the outside in. They observe the natural world, and then they create theories about how it should work. And reading Braitenberg's book, and looking at Braitenberg's vehicles, you might think that Braitenberg really favors and thinks that inventors have the advantage when it comes to interpreting and mimicking the natural world. Kind of like these inventors. This is Robotics Unlimited. And they are currently running a Kickstarter campaign to create the world's first commercially available legged robot. Let's look at it. The robot was biologically inspired, meaning it runs kind of like an animal would run. And that was kind of the key engineering detail that makes this thing really unique and interesting. And I think if I was in the woods and I saw this thing like scurry by, my first thought would be that, maybe it's not a robot, Maybe it's like a weird type of raccoon or something. Well, remember Maciek Albrecht. So he was the illustrator for Braitenberg's book. You see that? Looks a lot like that robot we just saw. But this book was written in the 1970s. It was probably before any of the founders of Robotics Unlimited were even born. So you have to ask yourself, when it comes to inventors and observers, who's really on the cutting edge of understanding and pushing our understanding of the natural world. As JavaScript developers, I think that we can occupy a space in between. I hope that I've showed you that we can create natural simulations. We can also code in opportunities to also be participants. Or we could just sit back and enjoy what we've created. Either way, I hope you've enjoyed this talk. and we had a great JSCamp. I'll see you at the pub. And these are some links, again, all the code for the demos you can find at that repo. And I will call out these two projects. Flora.js is a framework that I created to render the more complicated kind of Braitenbergish simulations. And then the super simple sim is just a very pared down implementation of that, and you can have fun with that. So thanks a lot.